Hello guys, so this is unsteady flowing pipe networks and we are starting a new material, unsteady one-dimensional compressible gas flow. Okay, so we have dealt with slightly compressible, that is liquid systems, we have dealt with open surface flows, and now we are dealing with gas flow. So we start off with the one-dimensional integral form of our equations, that is the continuity equation here, the equation of motion, and we'll also need the energy equation. So just to remind you, in the energy equation, E is the the energy content, that is the internal energy plus the kinetic term, and for an ideal gas, du is cv dt. On the right hand side, Q is the heat flux, tau is friction terms. You're familiar with these equations already. And we have four unknowns because we have density, velocity, pressure, and temperature or energy. So we'll need a fourth equation, which is some kind of state equation. Okay, so pressure and temperature. For an ideal gas, this is the ideal gas law. Okay. And then, as we already said, applying the divergence theorem, you can rewrite these equations in another form, which include only a spatial and a temporal derivative. So these ones are given here. Okay, and also the energy equation here. So this is very similar to what we have already done, and probably it's worth speaking about the solution strategies. So we will solve this set of equations by two techniques. The first one is the isentropic method of characteristics that I will provide today. And the other one is another general solution technique, which is called Lax-Wendroff scheme. Before we start anything, let's compare them. So the isentropic method of characteristics is a technique which is, as it says, it's isentropic. So you can have neither heat flux nor friction inside, because it should be isentropic. So it's adiabatic and reversible, thus there is you cannot model friction force with it. You cannot have heat exchange, but it's fairly simple, and one huge advantage is the shock waves are naturally included. This is something that you've already seen on the open surface flows, that water jumps, hydraulic jumps can very easily be handled and very accurately with these characteristics-based solvers. The Lax-Wendroff scheme will be a finite difference scheme, so any physical effect can be handled, heat flux, friction force, whatever you want to. The boundary conditions, I prefer to handle them with method of characteristics, but you'll have a problem here because as it's a finite difference scheme, it will oscillate around shock waves, so we will need artificial damping around shock waves. Okay, and then we start the isentropic method of characteristics. There's a bracket missing here. So as I said, we assume isentropic flow, so there is no heat transfer, and it's perfectly isolated, or the process is reversible, and the friction terms are also zero. Now, before we start doing anything, we make some preliminary calculations. So if it's an isentropic process, then you can develop equations that connect, for example, density and sonic velocity between any point in the flow rho and some initial state, rho node. Okay? And if you make this replacement, then the temporal and spatial derivative of the density can be replaced by something including the sonic velocity A. Okay, so now A stands for sonic velocity. So we can get rid of the density and use sonic velocity instead. Also, from the very definition of sonic velocity, you can replace the equation of motion with this equation. Actually, there is a typo here. The derivative is the same in both cases. Okay, good. Now, with this transformation, the continuity equation can be rewritten in this way. Okay, or this is equivalent of it. So basically, you replace the density by sonic velocity, and then you get an equation for sonic velocity and velocity. You can do the same with the equation of motion. Okay, so this is fairly simple because there is no density derivative. So this is simpler. As you see, the right-hand side is 0. And the energy equation is omitted because we don't need it. If you assume isentropic process, then you don't need the energy equation, because what would you use the energy equation typically is to compute the temperature. But if you know the pressure distribution, then making use of isentropic formulae, you can work out the temperature. So by assuming an isentropic flow, you basically get rid of the energy equation, and what you are left with is a continuity equation, an equation of motion, both in terms of velocity and sonic velocity, plus the ideal gas law, P over rho is R times T, plus the isentropic equations. Okay, and then again, if you mess around with this equation and this equation, you can easily derive characteristic equations. Okay, so again, you have something like now where is it? dA over dt plus something times dV over dt. Okay, so the characteristic equations look like this now. That again, the derivative of a Riemann invariant, which is beta, along special lines is 0, and now the Riemann invariant is A minus kappa minus 1 over 2 times V. Okay, so this is the same variable that was V minus 2C in the case of open surface flow, or P minus rho over V P minus rho A V for slightly compressible flows. Okay, and then the rest is very similar. Again, the characteristic lines are V plus A and V minus A, V plus A and V minus A, which means that essentially this is the very same technique as the one we use for open channel flow. So if we go back to open channel flow, we have the very same situation. Okay, so everything is the same, even the slope of the characteristic lines are the same. It's just that the characteristic quantities alpha and beta are different, because it's not V plus or minus 2C as it was, where is it? As it was here, V plus or minus 2C, but it's these quantities with kappa in them. Just a second. Here. So this quantity, and this here is alpha. A plus kappa minus 2 over V, and the A minus kappa minus 2 over V. Okay, so this is the third example of characteristic equations. It should look very similar by this time, because it's absolutely the same as for open surface channels flows. I will stop here, and next week I will post another video on handling the boundary conditions, which again will be similar to the open surface case, but for the sake of completeness I will provide all the equations that's needed. Thank you and bye-bye.